into one of the most audacious and genuinely mind-bending ideas at the frontier of physics, the ER EPR conjecture.
That pip one.
It really is. We've sifted through, well, a stack of groundbreaking research analyses, from papers by Einstein himself way back when, right up to the cutting-edge theoretical frameworks today.
All trying to untangle this question that's been, frankly, baffling physicists for almost a century now.
Exactly. And our mission here for this deep dive is to explore this really bold claim that the universe's large-scale structure, space-time geometry, the very fabric of reality might be intimately connected to that bizarre non-local quantum thing called entanglement.
It sounds wild when you put it like that.
It does. And you're about to discover how two sort of seemingly unrelated problems that really troubled Einstein might actually be two sides of the same coin. It could offer a kind of shortcut to understanding what some call the deepest gap in our grasp of reality.
So we'll be your guides through this, navigating the complex interplay between general relativity, GR, describing the universe on the biggest scales, planets, galaxies, the whole cosmos.
The smooth geometric stuff.
Right. And on the other hand, quantum mechanics, QM, which governs the microscopic world of particles and probabilities, will trace ER EPR from its twin foundations, both, believe it or not, from 1935.
Amazing coincidence, that.
Isn't it? Right up to its modern formulation within things like holographic duality. What's just fascinating here is how it seeks to bridge this enduring schism between these two monumental theories.
Suggesting they aren't just compatible, but maybe.
Maybe they're actually two different descriptions of the same underlying reality.
Okay, that's a huge claim. Let's unpack this fundamental challenge first, because it's really at the heart of everything, isn't it? This divide.
Absolutely.
On one side, we have general relativity, GR, the DeVaux-Rayleigh car. Think curved space-time, gravity as geometry, dictating the dance of planets and galaxies. It feels smooth, deterministic, predictable.
And then the other side. Quantum mechanics, QM. The world of particles, probabilities, and these, well, profoundly non-local connections that Einstein had such trouble with. It's discrete, probabilistic.
Fundamentally different languages.
Exactly. For nearly a century, these two have been, well, basically incompatible, creating this deep gap in our understanding, especially when we look at extreme places like inside black holes or think about the Big Bang, the very early universe.
Right. And historically, the search for quantum gravity, this unified theory, it often went down one of two paths, didn't it?
Yeah.
Either trying to, quantize GR,
De Grainy, yeah.
or trying to have GR somehow emerge from a more fundamental quantum theory.
But then a different idea started gaining traction, pulling from information theory, the whole it from bit concept.
It from bit, right?
Yeah.
Space-time from information.
Precisely. And this shift, it really moved the key question. It went from what is space-time made of to maybe how is space-time encoded?
Yeah.
And this conceptual shift, that's really the fertile soil where ER EPR grew. It offered a new angle on how these two pieces of physics might actually connect.
Okay, so here's where it gets really interesting.
Yeah.
2013, Juan Maldacena, Leonard Susskind, they dropped this, bombshell. The ER EPR conjecture.
A very bold, very elegant proposal, essentially saying maybe this schism, this gap is just illusory. Maybe we've been looking at it wrong.
And the core statement is just stark. ER equals EPR.
ER EPR. And the historical quirk is just amazing. Both ER and EPR came from papers Einstein co-authored in the same year, 1935.
It feels like physics poetry or something.
It really does, like history playing a long game.
So let's break that down. ER and EPR. ER is the Einstein-Rosen bridge. That's the wormhole, right? From general relativity.
For our old friend, yes. The theoretical tunnel through space-time.
And EPR is the Einstein-Podolsky-Rosen paradox. That's about quantum entanglement.
The spooky action at a distance.
Right. So the conjecture says any two quantum systems that are entangled, an EPR pair,
are connected by a wormhole, an ER bridge.
Wow. Not like a metaphor, but actually connected.
That's the proposal, an identity. Imagine that.
Let's dive into the ER side first then. What exactly is an Einstein-Rosen bridge?
Okay, so an ER bridge is a theoretical solution in GR. It's a tunnel-like feature in the topology of spacetime, popularly, a wormhole. Einstein and Nathan Rosen, they proposed it back in 1935.
But not for travel, originally.
No. Their idea was to represent elementary particles without hitting mathematical problems, singularities. That original motivation, though, it's now seen as, misguided.
So these aren't just science fiction plot devices. They're actual mathematical possibilities within GR.
Exactly. They arise quite naturally when you look at the math, specifically what's called the maximally extended Schwarzschild Schwarzschild geometry.
Which describes?
The space-time around a simple, non-rotating black hole. But the full solution, the maximal extension, includes not just the black hole we usually think of, but also a theoretical white hole, and crucially, two distinct universes or regions of space-time connected by this geometric throat, the ER bridge.
Okay, but the big question everyone asks, can you go through them?
Yeah.
Are they traversable?
Classically. Definitely not. They're incredibly unstable.
Like they collapse instantly.
Pretty much. Seminal work, Fuller and Wheeler back in the 60s showed they pinch off way too fast. Even light couldn't make it through.
So they snapshot.
Faster than light can cross. Which actually was seen as a good thing initially. It prevented paradoxes.
Ah, like time travel or faster than light signals messing up causality.
Exactly. If they were stable and traversable classically, you'd violate special relativity all over the place. So non-traversability kept things consistent.
So hypothetically then, what would it take to make one traversable, to hold it open?
Ah, that's where you need something truly exotic matter.
Stuff with negative mass or energy.
Essentially, yes. It would need negative energy density to create repulsive anti-gravitational effects, something to prop the throat open against that collapse.
Does that even exist?
Yeah. Well, quantum effects, like the Casimir effect, can produce tiny, localized negative energy densities. But getting a stable macroscopic amount, that's widely considered unphysical, not something we expect to find lying around.
Okay, so that's the wormhole side. Geometric tunnels, classically unstable, need exotic stuff to traverse. Now let's pivot to that other 1935 paper, Einstein-Podolsky-Rosen, EPR. Their challenge to quantum mechanics.
Right. The famous paper, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? A direct challenge.
What was their argument? It was a thought experiment, wasn't
It was. Imagine creating two particles, like electrons, so their properties, say their spin, are perfectly correlated. Then you separate them, send them miles apart.
Okay.
Now you measure the spin of one particle here. Quantum mechanics says you instantly know the spin of the other one way over there without disturbing it at all.
Instantly. That's
Yeah.
the key part.
That's the kicker, EPR argued. If you can measure spin along one axis here and know the result there, or measure along a different axis here and know that result there, then both results must correspond to pre-existing elements of physical reality for that distant particle.
Even though QM says you can't know both simultaneously for a single particle?
Exactly. So their conclusion was, QM can't describe all these elements of reality, therefore it must be incomplete. There must be some hidden information QM was missing.
And this is where Einstein's famous spooky action at a distance line comes in. He hated this non-locality.
Deeply uncomfortable with the randomness, sure, but especially this non-locality. This instantaneous influence between distant particles with no, signal traveling between them. He felt it had no place in a rational physical theory.
What Einstein saw as a paradox, a sign of incompleteness.
We now understand as a fundamental feature of reality, quantum entanglement. It wasn't a flaw in QM, it was QM telling us something profound and weird about the universe.
How did we get from paradox to accepted reality?
John S. Bell. His work in the 1960s was absolutely crucial. He took EPR's ideas and showed mathematically that the correlations predicted by QM entanglement are stronger than anything you could explain with classical local hidden variables, the kind Einstein hoped for.
He devised a test.
Yes. Bell's inequalities. It turned a philosophical debate into something you could actually test in the lab.
And the experiments.
Starting with Friedman and Clauser in '72, then Elaine Aspect's famous experiments in '82, and many, many more since then, the results are clear. Bell's inequalities are consistently violated, just as QM predicts.
So the spooky action is real.
It's convincing proof. Quantum entanglement is real. That spooky action is how the world works, even if we still grapple with what it fundamentally means. The deep mechanism is still a mystery.
Okay, so we have ER bridges, geometric tunnels from GR, and EPR entanglement, spooky quantum connections. The ER EPR conjecture slams these together, says they are one and the same.
Right, Maldacena and Susskind's central idea. Any pair of quantum entangled systems is connected by an Einstein-Rosen bridge. Not just analogous, but an identity.
An identity.
No.
So the claim is that space-time structure, its topology.
Is the physical manifestation, the dual of quantum entanglement.
So, wait, the, solid, reliable structure of space-time? It's built from these ghostly quantum connections. That's a huge leap.
It is a mind bender. It suggests that spatial connections, distance, geometry, the stuff that feels so fundamental, maybe it isn't. Maybe it's emergent.
Emergent, meaning it arises from something deeper.
Exactly. Woven from this deeper network of quantum correlations, Susskind and Matessina argued that without entanglement sewing space together, the universe would just atomize. It would fall apart into disconnected points.
Entanglement holds space together.
That's the core idea. It provides the connectivity.
And is this meant to apply everywhere, not just for, say, two halves of the black hole, but for any entangled particles?
Yes, the ambition is for it to be a universal principle. They speculate that even something simple, like a basic entangled state of two spins.
Like two electrons we entangle in a lab.
Exactly, that even they are connected by a bridge. Now, it wouldn't be a classical wormhole you could, fly a spaceship through.
Right.
It would be a highly quantum fluctuating connection, something much more subtle, buried in the quantum foam, maybe.
Okay, that's a radical idea.
Yeah.
What's the main evidence? Where does this confidence come from, especially if we can't just, see these tiny wormholes?
The primary support, really the birthplace of the idea in its modern form, comes from the ADA-CFT correspondence, anti-de Sitter conformal field theory.
That was Maldacina's big thing in '97, right? Holography.
Exactly. It's a concrete example of the holographic principle. It's this amazing mathematical equivalence, a duality between two very different-looking theories.
One's a theory of quantum gravity, living in a specific kind of spacetime called anti-z Sitter space.
Which has gravity, yes, in, say, d+1 dimensions.
And the other is a quantum field theory, without gravity, living on the boundary of that spacetime.
In d dimensions, yes. And the correspondence is like a dictionary. You can translate concepts and calculations between the two.
A gravity theory in the bulk and a quantum theory on the boundary.
That's the picture. And a key entry in this dictionary came in 2006, the Ryu-Takayanagi formula, or RT formula.
What did that show?
It showed something remarkable. The amount of entanglement, specifically the entanglement entropy, between different parts of the boundary quantum theory, is directly proportional to the area of a certain minimal surface hanging down into the bulk gravitational spacetime.
So entanglement on the boundary equals geometry in the bulk.
Precisely. Area is entanglement entropy. This was the first really solid quantitative link. Geometry encoding entanglement information.
And how does this connect directly to wormholes and black holes?
Well, consider a specific setup. The eternal black hole in 8S spacetime. This solution naturally has an Einstein-Rosen bridge connecting its two sides, or two exterior regions.
Right, we talked about that geometry.
In the ADA-CFT dictionary, the description of this eternal black hole on the boundary is a specific entangled state involving two copies of the conformal field theory, one for each side.
So the two CFTs are entangled.
And the bulk geometry connecting them has a wormhole. In this well-understood case, the wormhole is the geometric representation of the entanglement between the boundary theories.
Ah, I see. So ER EPR holds true in this specific calculable ADS-EFT example.
Exactly. The conjecture, then, is the bold step of saying, okay, maybe this isn't just an ADA-CFT thing. Maybe this equivalence, ER EPR, holds universally for all entanglement.
That makes sense. Generalizing from a working example. Are there simpler ways to picture this? Like toy models. My head is starting to spin a bit.
Yeah, it's abstract stuff. Yes, there are helpful models. Tensor networks are one example. They're mathematical structures used in condensed matter physics. But they visually show how you can build up something that looks like geometry purely from patterns of entanglement.
Like knitting space from entangled threads.
Sort of, yeah. Another really powerful idea is interpreting ADA-CFT itself as a type of quantum error correcting code, or QEC.
Like the codes used in quantum computing to protect information.
Exactly the same principle. The idea is that information deep inside the bulk spacetime is encoded redundantly across the boundary theory. Information isn't lost if you only look at a small piece of the boundary.
How does that help?
This QEC interpretation turns out to be crucial for resolving some of the paradoxes that pop up, like the black hole information paradox. It changes how we think about retrieving information.
Okay, so this conjecture, ER EPR, it's not just an elegant theoretical connection. It potentially offers real solutions to physics' big headaches.
That's its main draw, absolutely. Its power lies in its potential to resolve these stubborn paradoxes. It offers, as some put it, a topological escape hatch.
By changing how space is connected.
Exactly. By suggesting wormholes link things we thought were separate, it can dissolve contradictions.
The black hole information paradox is the classic example, right? Hawking's calculations showed information falling into a black hole seemed to be lost forever when it evaporated.
Which violates a core principle of quantum mechanics. Unitarity, the idea that information is always preserved, it was a huge crisis.
But at SCFT largely convinced people information must get out somehow.
Right. It shifted the paradox from if information escapes to how it escapes. But then things got even worse.
With the firewall paradox, AMPS.
Yes, AMPS. Ahmed Omhiri, Donald Meroff, Joseph Polchinski, James Sully. In 2012, they sharpened the problem dramatically.
What was their insight?
They looked closely at the entanglement requirements. For information to escape, a newly emitted Hawking particle, call it B, must be entangled with radiation that escaped much earlier, call it C.
Okay, B entangled with C. Makes sense for information preservation.
But T, general relativity's no-drama principle, says someone falling into the black hole should just sail smoothly across the horizon. For that to happen, particle B must also be entangled with its partner particle A that falls inside the black hole.
So B has to be entangled with C outside and D with A inside.
Exactly. But quantum mechanics has this strict rule, monogamy of entanglement. One particle can only be maximally entangled with one other system. It can't be fully entangled with two separate things.
Quantum polygamy is forbidden.
Precisely.
Sure.
So AMPS concluded something had to give. Their terrifying conclusion was that the no-drama principle fails. There must be a firewall at the horizon, a wall of high energy that incinerates anything trying to cross.
Which violates general relativity's smooth horizon idea. A huge clash.
A massive clash between QM and GR's core principles.
So how does ER EPR ride to the rescue here? How does it put out the firewall?
In their 2013 paper, Cool Horizons for Entangled Black Holes, Suskind and Maldacena used ER EPR to argue the firewall calculation was based on a wrong assumption about spacetime connectivity.
What was the flawed assumption?
The assumption that the inside particle A and the early radiation C were truly separate systems. ER EPR says, no, because A and C are entangled, they must be connected by a wormhole.
A wormhole connecting the black hole interior directly to the distant Hawking radiation.
Exactly. The black hole interior isn't isolated. It's linked to that cloud of radiation via potentially complex, multi-throated wormholes. Like an octopus, sometimes people say.
An octopus wormhole.
Okay.
And how does that help?
It dissolves the conflict. If A and C are connected by a wormhole, they aren't truly independent systems in the way the firewall argument assumed. This geometric connection is the entanglement. You no longer need the problematic entanglement between the outgoing particle B and the infalling particle A.
So A is entangled with C through the wormhole, B is entangled with C, the monogamy problem disappears.
The conflict evaporates. No need for AB entanglement, therefore no need for a firewall. The horizon can remain cool.
Wow, that's elegant. If it's right.
It's a very clever proposed resolution.
What about making wormholes traversable? We said classically they aren't and need exotic matter. Did ER EPR change that picture?
Well, yes and no. Within the context of AD-SCFT, further work, especially by Gao, Jafferis, and Wall, showed something amazing. You can make wormholes traversable under specific conditions.
Without exotic matter.
By engineering the boundary conditions. If you add a specific kind of direct interaction between the two boundary CFTs that are dual to the wormhole's bends, this interaction, viewed from the bulk, generates the necessary negative energy effect, like the Casimir effect, needed to hold the wormhole open just long enough for a signal to pass through.
So you can send something through.
Yeah.
But is it a shortcut? Can you beat light speed or travel in time?
Crucially, no. That's the key. The calculations show that sending a signal through this engineered wormhole still takes longer than sending it directly through the surrounding bulk space.
So causality is preserved, no time machines.
No time machines. It respects the fundamental speed limits of the universe. It's traversable, but not a shortcut.
And this links to quantum teleportation you mentioned.
Yeah, this is another fascinating connection. Sending a signal through one of these traversable wormholes, viewed from the gravity side, looks like teleportation from the boundary quantum theory side.
So the wormhole traversal is quantum teleportation.
It's interpreted as the gravitational dual of it. On the boundary, you insert a quantum state into one CFT, it gets scrambled, and then through that specific interaction between the two CFTs, the state gets reconstructed in the second CFT.
So the wormhole process mirrors the steps of quantum teleportation protocols.
Exactly. The wormhole's traversability corresponds to a well-defined physical process on the boundary. It gives the wormhole a kind of tangible operational meaning within that framework.
Okay, this sounds incredibly powerful.
Yeah.
Elegant solutions, deep connections. But you flagged serious problems too. A formidable array of hurdles, inconsistencies, objections. This is where the culture war comes in.
It absolutely is. The debate around ER EPR, especially its universal applicability, really highlights this fundamental schism in theoretical physics about, well, what counts as progress when direct experiments are maybe impossible for now?
What are some of the big conceptual or theoretical hurdles within the idea itself?
One major one is the no cloning problem. Quantum mechanics forbids perfectly copying an unknown quantum state.
Right, fundamental principle.
But if ER EPR implies a wormhole connects any entangled pair, naively, you might worry information could somehow be cloned by accessing it both directly and through the wormhole.
How is that resolved?
The proposed solution relies heavily on that quantum error correction idea we mentioned, the QEC framework.
The bulk info is encoded redundantly on the boundary.
Right. The idea is that information in the bulk corresponds to logical quantum operators, and different ways of accessing it from the boundary are just different ways of decoding the same logical information, not cloning it. But
it means the whole consistency relies on QEC working exactly right in this context.
Precisely. It makes the conjecture critically dependent on the validity and applicability of the QEC framework, which is still an active area of research and not fully proven in all necessary contexts.
Okay, what else? You mentioned non-detectability.
Yes, the non-detectability dilemma. There's a theoretical result showing that from the outside, you can't locally tell if a black hole has a wormhole connecting it to another region, a two-sided black hole, or if it's just a regular one, one-sided.
You can't just poke it and see if there's another side.
Not locally, no. This is actually seen as a good thing, a rescue for ER EPR. Because if you could detect the wormhole locally, it would likely violate fundamental principles of quantum mechanics, like linearity.
Okay, so it's consistent with QM because you can't see the wormhole directly.
But the flip side is that this very non-detectability makes the core claim that the wormhole is there fundamentally hard, maybe impossible to verify directly.
Which leads to accusations of it being non-falsifiable, untestable.
Exactly. Critics argue it puts the conjecture in a difficult spot epistemologically.
So, theoretically tricky, hard to test directly. What happens when you try to apply it beyond eddy CFT to the real world, like to simple particles?
This is where things get, quantitatively problematic, where the phenomenological inconsistencies arise, and they arise spectacularly, as some sources put it.
Okay, hit me with it. What happens with, say, a simple entangled electron-positron pair?
Right. If you take ER EPR seriously for this pair, and you try to estimate the properties of the wormhole connecting them using standard physics formulas like the Bekenstein-Hawking entropy formula relating geometry and information,
you get a prediction for the wormhole's mass or size.
You do. And the predicted mass for the wormhole connecting a simple electron-positron pair is, wait for it, approximately 124 times larger than the actual combined mass of the electron and positron themselves.
10 to the 24, that's astronomical. A billion times heavier.
It's a staggering discrepancy, completely nonsensical from a physical perspective.
Okay, that's bad. What about speed?
Similar problem. If an entangled photon is dragging this hypothetical wormhole connection, ER EPR implies it should have an effective mass.
Meaning it wouldn't travel at the speed of light, see?
It should travel slower than c. But experiments, high-precision tests of relativity put incredibly tight constraints on any deviation from c for photons.
How tight?
The limits imply an upper bound on any such wormhole mass that's roughly 32 orders of magnitude smaller than what the naive ER EPR calculation predicts for entangled photons. Another massive mismatch.
So basically, if ER EPR applied straightforwardly to everyday particles, we should see entangled things being vastly heavier and slower than they are.
That seems to be the implication of the direct calculation, yes. The predicted wormhole mass, around 10 to 9 kilograms, is actually gravitationally significant on a lab scale.
So you could weigh entanglement. Or see mass anomalies.
Potentially, yes.
Yeah.
A collection of entangled pairs should have a measurable weight difference. Even a single entangled ion might show a mass shift detectable by modern mass spectrometers. And, of course,
no such effects have ever been observed.
Not a hint. Ever.
So what do proponents say about these? Well, these glaring quantitative failures when applied to simple systems.
The standard response, the rebuttal, is that the wormhole connecting simple particles isn't a classical or semi-classical object like the ones described by Bekenstein-Hawking formulas. It's a highly quantum object.
Meaning the formulas don't apply, so the calculation is wrong.
Essentially, yes. That you can't use those tools to estimate its properties, but critics tend to see this as
the convenient excuse.
A strategic retreat into non-falsifiable territory. protecting the conjecture by saying it only applies where it's too quantum to calculate or test directly, making it ill-defined in the regimes where it seems to fail.
Okay, so given these deep conceptual issues and these massive phenomenological problems, what is the status of ER EPR in the physics community overall? Is it seen as the leading candidate for quantum gravity?
Oh, definitely not universally accepted. Far from it. It's deeply polarizing.
Polarizing how?
Well, there's a significant group, particularly those working within or close to the AD-SCFT framework, who find it incredibly powerful and insightful, a key organizing principle. But there's also a large portion of the community, perhaps even a majority outside that specific area, who view it as highly speculative, ill-defined, even ugly and ad hoc.
Ugly and ad hoc. Strong words.
Yes. There's real skepticism about its universality and physical relevance beyond AD-S.
And is there some truth to the hype versus science criticism I've heard?
That criticism definitely exists. Some argue that the certainty with which ideas like ER EPR are sometimes promoted, especially to the public or broader scientific community, isn't always aligned with their actual tentative scientific status.
An overselling of speculative ideas.
Well, that's the charge. That it can feel like advertising masquerading as science, possibly stemming from the culture around string theory, needing to show progress on fundamental questions.
And what about this scaffolding argument? That the string theory connection isn't always essential.
Right. This is the idea that while string theory and AD-SCFT provide the context and motivation for ideas like ER EPR, sometimes the final valuable calculations or insights don't strictly depend on the full string theory apparatus.
Like you could derive the result without the strings.
In some cases, yes. The argument is that the strings can be removed like scaffolds after the building is constructed. This leads to questions about how essential the underlying framework really is versus how the research program is marketed.
So taking all this into account, perhaps the most balanced view is that ER EPR is powerful, maybe even correct.
But likely only within that very specific, highly idealized context of the AD-SCFT correspondence, that theoretical laboratory.
And the problems arise when you try to take it out of the lab and apply it everywhere.
That seems to be where the vast majority of the inconsistencies and paradoxes appear. When this niche principle, which works beautifully in AD-SCFT, is extrapolated and claimed as a universal feature of nature, applying to any old entangled pair in our actual universe, that's where it runs into trouble.
Okay, so wrapping this up, where does this leave us? ER EPR is clearly a profound, influential idea, no doubt about that. It elegantly ties together two key concepts from that pivotal year, 1935.
Einstein's wormholes and his spooky entanglement.
Offering this powerful new lens on the universe. Its success is undeniable in stimulating new research directions, providing fresh angles on really hard problems, like the black hole information mess.
Absolutely. Its conceptual power is huge, but its weight against these, frankly, overwhelming challenges that really call its status as a physical theory of our universe into serious question.
Its main support is from AD-SCFT, a different kind of universe.
Right. A universe unlike ours, its consistency seems to rely on this QEC framework, which isn't fully proven, and the phenomenological front, the comparison with reality,
is pretty stark. Predictions off by dozens of orders of magnitude.
Exactly. Those quantitative disagreements are hard to ignore.
So, bottom line, in its current form, ER EPR isn't really a theory of our universe.
It seems not. It's probably best understood as a powerful guiding principle, maybe a specific dictionary entry that holds true within that idealized theoretical lab of AD-SCFT.
A conceptual tool, a source of insights, a bridge between fields.
Yes, its value has definitely been immense in those ways. It sparked creativity and connected ideas.
So what's next then? Where does ER EPR go from here?
Well, the challenge for proponents is clear. They either need to find a robust way to translate the principle from anti-de Sitter space, where it works so well, to our actual universe, which looks more like de Sitter space.
Or maybe discover a completely new formulation.
A new formulation that somehow resolves those massive phenomenological problems, those quantitative failures, without just retreating into it's too quantum to calculate territory, without becoming non-falsifiable.
That's a tall order.
It is. Until then, ER EPR remains this beautiful, provocative, and deeply contentious idea at the very frontier of the human search for a unified understanding of reality.
A beautiful, contentious idea. I like that. And it leaves us with a final thought for you, the listener. If the very fabric of space-time is somehow woven from quantum entanglement, but the connections we know exist between distant particles be just a faint echo, a hint of some underlying cosmic web binding everything together in ways we haven't even begun to grasp yet, something to ponder.